NASA built a material designed to destroy itself, and then put 4 human beings behind it. That is not a critique. That is the engineering specification. The Orion heat shield does not protect the crew by being impervious to the entry environment. It protects them by sacrificing itself in a controlled and precisely engineered sequence of thermal decomposition that carries the heat of a 5,000-degree plasma environment away from the crew module in the mass of its own disintegrating surface. The shield works by dying. The question that the Artemis I inspection data raised, and that the Artemis II mission has now put to the test with 4 living people inside the capsule, is whether the dying happens in the controlled and precisely engineered way the models predict, or whether it happens in the chaotic and unpredictable way that material physics sometimes produces when the conditions exceed what ground testing can fully replicate. That question does not have a conspiracy framing. It does not require suppressed evidence or classified leaks or fabricated anomalies in recovered images. It is sitting in the published technical literature in the precise and careful language of aerospace engineers who found something they did not expect on the Artemis I heat shield and who spent 2 years trying to understand it well enough to be confident that the crew of Artemis II would come home. The horror in this story is not a cover-up. The horror is the math. And the math is genuinely terrifying. The Orion capsule's return from the translunar trajectory begins at the entry interface, the point approximately 120 kilometers above Earth's surface, where the atmosphere is dense enough to begin producing measurable aerodynamic forces on the descending vehicle. At that point, the capsule is traveling at approximately 39,000 kilometers per hour. The physics of what happens next are not complicated in their broad outline, but are extraordinarily complex in their specific details. The air molecules in the capsule's path cannot move out of the way fast enough. They stack up ahead of the vehicle in a shock wave that compresses the gas adiabatically, converting the kinetic energy of the compression into thermal energy with an efficiency that produces temperatures in the shocked gas layer ahead of the heat shield that reach approximately 5,000 degrees Fahrenheit at peak heating. The heat shield surface is exposed to this thermal environment for several minutes during the entry sequence. The ablative material must absorb, decompose, and carry away sufficient thermal energy during those minutes to keep the temperature of the structural layer behind it within survivable limits for the crew module and within operational limits for the systems that the crew depends on. The margin between the thermal energy the shield is designed to handle and the thermal energy that would compromise the structural layer is the number that determines whether 4 people come home. That number is not published in press releases. It is in the engineering specifications, and the Artemis I data revealed that the real thermal environment during a skip entry from lunar distance is not identical to the environment that the pre-flight models predicted. The specific finding from the Artemis I heat shield inspection that the engineering community spent 2 years analyzing is documented in NASA technical reports and was discussed in briefings to the NASA Advisory Council. The phenomenon is called char liberation, and it is distinct from the normal ablation process in ways that matter to heat shield performance. In normal ablation, the carbonized char layer that forms at the surface of the avcoat material remains attached to the underlying virgin ablative compound as it builds up, providing the insulating function that is central to the shield's thermal protection mechanism. In char liberation, pieces of the char layer detach from the underlying material and are carried away by the aerodynamic shear forces of the hypersonic flow before they have provided their full insulating function. The detachment exposes fresh ablative material to the thermal environment earlier than the model predicts, increasing the local ablation rate in the affected region and potentially reducing the total thermal protection capacity of the shield if the liberation events are numerous or large enough. The Artemis I inspection found char liberation events across portions of the heat shield surface. The investigation into their cause identified the specific mechanism as related to the 2-pulse thermal loading of the skip entry, where the partial cooling interval between the first and second atmospheric contacts produced thermal stress in the char layer that reduced its adhesion to the underlying material and made it more susceptible to aerodynamic detachment during the second contact's peak heating phase. The models had not fully captured this mechanism because the 2-pulse skip entry thermal environment had no precise analog in the ground test database. Real flight produced a real finding that ground testing had not predicted. That is not a failure of engineering diligence. It is a demonstration of why flight testing exists. It is also the reason that the margins of confidence in the Artemis II heat shield performance are defined by the quality of the engineering response to that finding rather than by a validated model with multiple confirming flight tests behind it. The engineering response involved several parallel workstreams. The thermal models were updated to incorporate the char liberation mechanism and its dependence on the two-pulse loading profile. The AVCOAT application process was modified to improve char layer adhesion characteristics. The entry trajectory was assessed to determine whether adjustments could reduce the thermal stress during the interpulse cooling interval. The flight rationale for proceeding with crew was established based on analysis showing that the updated models predicted acceptable performance margins, even accounting for the char liberation mechanism. All of this work was reviewed by NASA's technical authority chain and by the independent technical review boards that evaluate readiness for crewed flight. The process was thorough. The findings were documented. The rationale was established. And the Artemis II mission flew on confidence built from one real flight data point, an extensive analytical response to that data point, and modified hardware whose performance under the actual skip entry thermal environment had never been directly measured. The Artemis II heat shield inspection is the measurement. The inspection results will tell the engineering community whether the 2 years of analysis and design modification produced a shield that performs as the updated models predict. For the Artemis III crew, those results are not academic. They are the foundation of the safety case that will govern the design of the shield that brings them home. Inside the capsule during the 6 minutes of the entry sequence, while the heat shield is managing the thermal environment outside, the crew is managing the biological reality of the deceleration forces inside. The G-loading profile of the skip entry produces sustained acceleration forces that reach approximately 7 times normal gravity during the second atmospheric contact. 7G is not a number that describes a transient spike lasting fractions of a second. It describes a sustained load maintained for a period measured in tens of seconds to minutes as the capsule decelerates through the peak heating phase of the second contact. The human cardiovascular system has a well-characterized response to sustained high G loading and a well-characterized failure mode when that response is insufficient. The failure mode is GLOC, G-force-induced loss of consciousness. The mechanism is straightforward. At high G loads, the effective gravitational gradient between the heart and the brain increases. The heart must generate sufficient pressure to push blood upward against this increased gradient to maintain cerebral perfusion. If the heart cannot generate sufficient pressure, or if the pressure it generates is insufficient to overcome the venous pooling in the lower body that high G loading produces, cerebral blood flow drops below the threshold required to maintain consciousness. The visual system is the first to be affected, producing a progressive narrowing of the visual field called grayout that precedes the complete loss of consciousness called blackout if the G loading continues without relief. A crew member experiencing GLOC loses not just consciousness but the muscle tone required to maintain their position and operate their controls. They are functionally incapacitated for the duration of the GLOC episode and for a recovery period after G loading is reduced. The cardiovascular system of the Artemis II crew at the moment of peak G loading during the second atmospheric contact is not the cardiovascular system that those crew members had on the morning of launch. 10 days of microgravity has changed it. The cardiovascular adaptations to weightlessness begin within the first hours of spaceflight and are progressive over the duration of the mission. Plasma volume decreases as the fluid redistribution of microgravity reduces the cardiovascular system's assessment of its circulating volume requirement. Cardiac output decreases in response to the reduced peripheral resistance of weightlessness. The regulatory mechanisms that maintain blood pressure against gravitational gradients are less active because the gravitational gradient they evolved to manage has been absent for 10 days. The cardiovascular system that must maintain cerebral perfusion against 7G at the end of the Artemis II mission is a system that has spent 10 days adapting to 0G. The anti-G provisions built into the Orion crew survival suit apply external pressure to the lower body to reduce venous pooling and assist venous return to the heart. The training protocols for G tolerance include techniques for increasing intrathoracic pressure that improve cardiac output under G loading. These provisions are effective, and the mission designers have built margins into the G loading profile to account for the deconditioning effect of 10 days in microgravity. The margins are real. They are also the product of models built on ground-based centrifuge testing and short-duration spaceflight data rather than on measurements of actual cardiovascular performance during skip entry G loading after 10 days in lunar space. The Artemis II mission physiology data will provide those measurements for the first time. The crew members are not just astronauts during the entry sequence. They are the subjects of an experiment whose results will inform the cardiovascular protection protocols for every future deep space crew. The capillary hemorrhages visible in the whites of the eyes of returning astronauts, the petechial bleeding produced by the combination of high G loading and the cardiovascular changes of spaceflight, are the most visible biological record of what the entry physics demands from the human body. They are not dangerous. They resolve over days. They are the body's receipt for the transaction. Evidence written in the most accessible soft tissue of the face that the 6 minutes extracted something measurable from the people who passed through them. The medical teams at the recovery site will document them photographically as part of the post-mission health assessment. They will be quantified alongside the dosimetry readings, the cardiovascular measurements, the neurocognitive assessments, the bone density measurements, the immune function markers, and all the other biological data points that together constitute the complete record of what the translunar environment and the entry protocol cost the crew. That record will be published in NASA's Human Research Program reports and in peer-reviewed journals. It will be read by the mission designers planning Artemis III and by the flight surgeons who will certify the Artemis III crew for flight. It is the real document, more important than the panoramic photographs and more consequential than any press release. The complete forensic record of what it cost 4 people to go to the moon and come back in a vehicle making this journey for the first time with human beings inside it. When the capsule was recovered from the Pacific and the initial crew medical assessments were complete and the engineering teams had their first access to the hardware, the heat shield inspection began. The recovery teams working around the returned capsule were not in hazmat suits because of alien contamination or undisclosed biological agents. They were following protocols developed for the very real chemical hazards present in the recovery environment. The hypergolic propellants used in the Orion service module and reaction control system are toxic compounds whose combustion products and residuals require appropriate handling precautions. The ablated heat shield material contains compounds produced by the high-temperature decomposition of the Avcoat formulation that require characterization before the hardware is handled without protection. These are documented engineering realities of working with a returned spacecraft. They are not dramatic in the conspiratorial sense. They are the unglamorous chemical reality of what space hardware is made of and what it becomes after 6 minutes in a 5,000-degree plasma environment. The recovery procedures account for them with the same systematic thoroughness that the mission planning accounts for every other hazard in the mission profile. The inspection of the heat shield that follows recovery is the most consequential engineering activity of the entire post-mission period. Photographs of the complete shield surface. Measurements of char depth at a grid of sampling locations across the shield. Documentation of any regions where the ablation pattern or the char liberation events depart from the updated model predictions. Laboratory analysis of material samples. Comparison of the actual ablation pattern against the pattern predicted by the models that were updated in response to the Artemis I findings. This comparison is the test of 2 years of engineering work. If the Artemis II shield shows the same char liberation pattern as Artemis I despite the design modifications, the modifications were insufficient and the root cause analysis needs revision. If the Artemis II shield shows reduced char liberation consistent with the updated models, the engineering response was effective and the confidence in the model for future missions increases accordingly. If the Artemis II shield shows a different pattern than either the Artemis I findings or the updated model predictions, the engineers have new data that requires new analysis and the confidence margins for Artemis III depend on how quickly and how completely that analysis can be completed. Every possible outcome of the inspection has direct implications for the people who will fly on future missions. The inspection is not the end of the story. It is the beginning of the next chapter. The chapter in which everything the Artemis II mission cost in engineering risk and human biological exposure is converted into the knowledge that makes the next mission marginally safer and the mission after that marginally safer still. That is how aerospace engineering works. That is what the heat shield audit actually is. Not a cover-up. Not a classified revelation. A systematic and consequential process of learning from the real performance of real hardware in the real environment for which it was built, conducted by real engineers whose work will determine whether the next crew comes home. The horror is not what they found and suppressed. The horror is the math of what they are trying to get right. And they are still working on it.
NASA called these photos a triumph. They released them with press statements about inspiration and a new generation of explorers and humanity's return to the moon. And when I first saw them, I understood why. The resolution is extraordinary. 8,000 pixels of lunar surface rendered with a clarity that makes the moon look close enough to touch. The Shackleton crater at the lunar south pole rendered in a contrast so sharp that the boundary between the sunlit rim and the permanently shadowed interior looks less like a geological feature and more like a wound that never healed. These photos are genuinely extraordinary, but the longer you look at them, the longer you sit with what they actually show rather than what the press release says they show, the more the triumph narrative starts to develop cracks, because these photos are not just images of a beautiful, desolate landscape. They are a technical document, a record of an environment that the 4 human beings aboard the Artemis II spacecraft flew through at 49,000 kilometers per hour while their bodies absorbed radiation, while their suits kept the vacuum from reaching their skin, while the engineering between them and the most hostile surface in the accessible solar system held its margins. When you look at these photos as a technical document rather than an inspiration poster, what they show is not a destination, it is a threat assessment. The Shackleton crater, because the crater is the reason the Artemis program is targeting the lunar south pole in the first place, and because the photos of it reveal something that the mission briefings discuss in careful technical language that most public reporting does not translate into plain terms. The permanently shadowed regions inside Shackleton and the other craters at the lunar south pole have not seen direct sunlight for potentially billions of years. The temperatures inside these shadows, measured by orbital instruments and confirmed by surface probe data, sit at approximately 40 Kelvin, 40 degrees above absolute zero, cold enough that volatile compounds, including water ice that arrived via comet and asteroid impacts over geological timescales, have been preserved rather than sublimated away. This is why the South Pole matters. The water ice confirmed in these permanently shattered regions is the resource that makes a sustained lunar presence economically and logistically viable. Water for drinking, water electrolyzed into hydrogen and oxygen for propellant, water as radiation shielding mass. The presence of water ice at the lunar South Pole is not speculation. It is confirmed by multiple independent instrument packages on multiple orbital platforms. The photos show the surface above these deposits. They show the terrain the Artemis surface missions will need to navigate to reach them, and they show, if you are looking at them as a field geologist rather than a public affairs officer, exactly how difficult and exactly how dangerous that terrain is. The lunar regolith visible in the high-resolution images is not soil in any sense that the word implies familiarity or safety. The texture visible at 8,000 pixel resolution confirms what the Apollo sample analysis established and what every subsequent remote sensing measure measurement has reinforced. The surface of the moon is covered in a material that has been produced by 4.5 billion years of impact events occurring in the complete absence of the atmospheric and hydrological processes that round and smooth and chemically alter terrestrial sediment. Every grain in the images is the direct product of fracture, angular, sharp-edged, electrostatically charged by continuous solar wind bombardment, sized in the range that penetrates deepest into the respiratory system when inhaled, and chemically reactive at its surface in ways that make it biologically aggressive to soft tissue in a manner that has been compared in the peer-reviewed literature to asbestos exposure. The photos show this material covering every surface in the frame. They show it coating the rims of small craters. They show it accumulated in the low points of the terrain in deposits whose depth is difficult to determine from orbital imagery, but whose extent is total. The Artemis surface crews will be moving through this material. It will coat their suits. It will work its way into every joint and seal and mechanism through the electrostatic attraction that makes lunar dust one of the primary unresolved engineering challenges of the entire program. The photos document the problem. The solutions are still being validated. The shadows in the images deserve more attention than they typically receive in public discussion of the Artemis imagery. On Earth, shadows are temporary. The sun moves, the angle changes, the shadow shifts, and eventually the terrain it covers receives direct illumination. On the moon, in the regions near the poles that the Artemis program is targeting, some shadows are permanent. The geometry of the moon's axial tilt, which at approximately 1.5 degrees is nearly perpendicular relative to the plane of its orbit, means that the sun never rises more than 1.5 degrees above the horizon at the poles. Craters with walls high enough to block this near-horizon sun create interiors that are in permanent shadow. Permanently, not seasonally, not for geological epochs. Permanently, for as long as the crater has existed in its current form. The interior of Shackleton crater has not seen direct sunlight for perhaps 3 billion years. The images show this shadow as a hard geometric edge where the sunlit rim meets the interior darkness. Instruments can measure temperature and volatile content inside these shadows by indirect means. Cameras cannot image inside them with visible light because there is no visible light there. The darkness in these images is not a photographic artifact. It is the real absence of photons in a region that has been lightless for longer than complex life has existed on Earth. When the Artemis crews descend into these regions to access the water ice deposits, they will be working in artificial illumination inside a darkness that predates the evolution of the human visual system by billions of years. The photos show exactly where that darkness begins. The edge is sharp and it does not move. Now consider what the photos do not show. The radiation environment that the crew of Artemis II flew through during the lunar flyby is invisible to any optical instrument. The cosmic ray flux passing through the capsule hull and through the crew members' bodies at a rate that their dosimeters were recording continuously cannot be imaged. The solar energetic particle environment that the current solar maximum is generating at elevated intensity relative to any Apollo mission is not visible in an 8,000 pixel image of the lunar surface. The Van Allen radiation belts that the crew passed through twice, once on the outbound trajectory and once on the return, are not in the frame. The photos show the surface of the moon with extraordinary clarity. They do not show the environment between the surface and the crew. That environment is documented in the mission's radiation exposure records, in the dosimetry data that will be published in the post-mission health assessments, in the blood sample analyses that will measure the biological response to the radiation exposure the crew accumulated over 10 days in deep space. The photos are the visible record. The dosimetry is the invisible record. Both are part of what the mission documented. The press releases discuss the photos. The post-mission medical literature will discuss the dosimetry. The gap between those two conversations is where the real technical audit of what the crew experienced lives. The far side pass is the portion of the mission that the photos from the flyby make most vivid, and that the mission timeline makes most stark in terms of what it required of the crew and the hardware. During the period when the Orion capsule passed behind the moon and the moon's mass blocked all direct radio communication with Earth, the crew was operating in a communication blackout that lasted between 30 and 50 minutes, depending on the specific trajectory. Not a degraded communication link, not a high-latency connection, no connection. The deep space network antennas that had been tracking the capsule continuously since departure were receiving nothing. The mission controllers at Johnson Space Center were monitoring the last known telemetry state of the vehicle and waiting. The crew inside the capsule was executing their observation schedule, operating their cameras and science instruments, managing the capsule systems, and doing it all without the ability to report anomalies, request guidance, or confirm that their planned actions were consistent with what the ground teams would recommend given current system states. The autonomy that the Farside Pass required of the crew is not a capacity gap that training fills completely. It is a fundamental constraint of the mission geometry that places the crew in a position where they are the entirety of the decision-making capacity available to the mission for the duration of the blackout. The photos taken during the Farside Pass are the product of that autonomous operation. They are images taken by 4 people who were, at the moment of acquisition, the farthest from help than any human beings who had ever existed. The faces in the mission photos are worth examining as carefully as the lunar surface photos, not to look for signs of undisclosed biological harm, which is not what the images show, but to look for what sustained deep space exposure actually does to human faces in ways that the physiology of the environment predicts and the photos confirm. Fluid redistribution in microgravity produces the characteristic facial puffiness that astronauts experience within hours of entering weightlessness, as the fluid that gravity normally pools in the lower body redistributes toward the upper body and head in the absence of the gravitational gradient. 10 days of this redistribution is visible in comparison photos taken before launch and during the mission. The eyes of crew members who have been in microgravity for extended periods show the effects of the intracranial pressure changes that fluid redistribution produces, a phenomenon that NASA's Human Research Program has been studying intensively because in longer duration missions, the intracranial pressure elevation can produce visual impairment and structural changes in the optic nerve that persist after return to Earth. The skin tone changes visible in long-duration spaceflight photography reflect the cardiovascular adaptations of the body to the microgravity environment. None of this is concealed information. All of it is published in NASA's Human Research Program documentation and in the peer-reviewed literature on spaceflight. The faces in the photos show people who have been in space for 10 days. The physiology of 10 days in space is documented and measurable, and